So real quickly, here are some of the rules for limits that you should know. I think these are all pretty self-explanatory. You should have known these all from previous years, the last like 10 years of learning about calculus. If you have a limit of a function plus another function, you can separate into two different limits. If you have a limit of a function times a function, you can separate into two different limits. If you have a limit of a function divided by another function, you can separate it into two limits as long as the denominator 1 doesn't equal 0. If you have two functions separated by a subtraction sign, you can separate into two limits. And most importantly, well, maybe not most importantly, but equally as important, if you have a constant times a function, you can take the constant and pull it outside the limit. Everybody good with all of those? Everybody remember all of those? Hopefully. Yes, no, maybe.
Yes.
Yes, good. Okay, great. Also, yeah, I'm not going to give you guys a bunch of time to write all this down because it's all easy and you should be able to go back and write it down later if you want to. If I have a function being raised to a power, I can pull that power outside of the entire limit. Everybody good there? So I could rewrite this as limit as x approaches 2 of 3x plus 4, all raised to the 5th power if I wanted to. Easy enough?
Yes.
All right, cool. So those are the 6 rules for limits. I think there were 6 of them that we really need to be able to utilize. So we will start doing that in a little while. Once we talk a little bit about the sandwich theorem or the squeeze theorem. And hopefully you all remember what that is. The sandwich theorem or the squeeze theorem says that if I have one function that has been sandwiched between two other functions, so that let's say h of x is the one sandwiched, h of x is always greater than or equal to f, and it's always less than or equal to g on some open interval containing the a value that we're interested in, except maybe at a, because we could say maybe those don't exist at a. Then if the limit of the upper function is equal to the limit of the lower function at a, then that must also equal the limit of the function that is sandwiched in between the other two. This is the sandwich theorem or the squeeze theorem. Okay. Everybody good with that or no?
Yes.
Conceptually, spectacular. All right, let's do a problem or two. If we want to use the sandwich theorem to prove that the limit as x approaches 0 of x squared sine of 1 over x squared is 0, what should we do to begin with? That's right. We should begin by setting up an inequality. What inequality should we start with?
Sine of whatever that is -1 and 1, or with the thingies.
Yes, that, yeah.
Or sorry,
of whatever that
-1 is less than sine of the stuff, and then put the 1 on the other side.
All right, perfect. Yeah, we should know that that inequality should be true for any sine or cosine function, no matter what the angle is. And then all we gotta do is just multiply by the x squared. And now, if the limit on the left equals the limit on the right, which they both do, they both equal 0, then by the squeeze theorem, the limit of the function that has been sandwiched between them is also 0. Good or no?
Great.
Wonderful. All right. Let's not do this one. Let's change this into x to the third. Let's make this x to the third power. Just to make things slightly more complicated. Because why not? We can. What should we start with?
An inequality.
That's right, a very similar inequality to the one we just had, right? Cosine of 1 over the cube root of x is less than or equal to 1, greater than or equal to -1. Everybody good with that?
Yes.
All right. Now the problem begins when we try to multiply by,
X cubed,
and why is that a problem?
because it's less than -1. Wait, hold on. It's, yeah, it's less than -1 as you keep going to the negative infinity.
Yeah, that's true, right? And the big issue is that we're dealing with an inequality, right? And an inequality, when you multiply it by something, if that thing is positive, no problem. But if that thing is negative, it becomes a problem, doesn't it? You got to flip
Yes,
the
sir.
inequality signs if you multiply by a negative. So we're going to have to note that when x is greater than 0, x cubed is greater than 0, and there's no issue. But that when x is less than 0, x cubed is less than 0, and then there's an issue. So we'll have to do for x greater than 0, negative x cubed is less than or equal to x cubed cosine 1 over that cube root of x, less than or equal to x cubed. But for x less than 0, negative x cubed is greater than or equal to x cubed cosine 1 over cube root of x, which is greater than x cubed. Everybody agree with that? Good with that?
Yes.
All right, wonderful. So on this one where x is greater than 0, I just need to find the limit as x approaches 0 of negative x cubed and x cubed, right?
Yes.
Yeah, but what's the problem with that? If x is only greater than 0, I can't have a two-sided limit. I can only have a limit as x approaches 0 from the,
Wait, which one are we talking about?
or x greater than 0.
Oh, X greater than there is from the right side.
That's right, because x is positive. And that limit is 0, as is the limit as x approaches 0 from the right of x cubed, telling us that the limit as x approaches 0 from the right of x cubed cosine of 1 over cube root of x is also 0. But that's only the limit as x approaches 0 from the right. So then we got to do it about from the left. And that one we can only do using the left-hand limit with the one where x is less than 0. And lo and behold, those limits are both 0 from the left, telling us that by the squeeze theorem, this limit from the left is also 0. And so what? Since the left-hand limit and the right-hand limit are equal, that tells us that the two-sided limit must exist and it must have the same value. Good or no?
Great.
Wonderful. I am so glad that that is great. Nobody's got any issues, any complaints, any questions, any problems, anything? All right. Let's see if we can use the sandwich theorem to prove this limit, that the limit as x approaches 0, sine x over x is 1. I know we could do it really easily using L'Hopital's rule, but tough luck, you can't. Anybody remember how we did this last year? We should have proven this last year. Pretty sure we drew an angle in here and called that angle x, right? Because we have sine of x. And we said that this was a unit circle. And if this is a unit circle, then that's 1, as is this. And what is the height of this little triangle I got in here if I say that these are all right angles here?
The smaller one is sine, right? The smaller, like y component.
This y component you're talking about, yeah?
Yeah, that one.
Yep, that one is sine x. And the reason that's sine x is because the coordinates of this point should always be cosine x, comma, sine x. So the height that we've gone up from the x-axis is sine x. And that should tell us that the area of that triangle in red, which I didn't draw very well. That's better. What's that area? 1/2 the base of 1 times the height of sine x. So we got the area of that triangle. And then we should be able to figure out the area of the sector of this circle. What's the area of the sector of a circle? The area of the sector of a circle is the number of radians of that sector out of 2 pi for the whole circle times the area of the circle, right? Pi times the radius squared. And what does that give us?
X over 2.
X over 2. So the area there is 1/2 x. And what about the area of the big triangle outside? It ought to be, what's the height here?
1.
No,
Tangent of x, right?
it ought to be tangent of x, because the tangent of this angle ought to be opposite over adjacent. And if this is a unit circle, the base is 1. And so this other length ought to be tangent of x. So that area is just 1/2 tangent x. And just by the nature of this drawing, the red triangle better have an area less than the blue sector, which better be less than the big green triangle on the outside. And we should be able to build sine x over x inside this inequality to prove that this limit is 1. So first we'll multiply everything by 2. Sine x is less than or equal to x is less than or equal to tangent x. And then we're going to divide everything by sine x to put a sine x in this interior piece here. And that ought to give me 1 is less than or equal to x over sine x is less than or equal to 1 over cosine x. Good so far?
Yes.
Okay. And now all we have to do is take a reciprocal. Anytime you take the reciprocal of an inequality, flip the inequality signs. And what is our limit as x approaches 0 of 1? It ought to be
1.
1. And the limit as x approaches 0 of cosine of x ought to be the cosine of 0, which is
1.
1. And therefore, by the squeeze theorem, the limit as x approaches 0 of sine x over x equals 1. And what other one should we know that's related to this? The reciprocal of it. The limit as x approaches 0 of x over sine x is also equal to 1. And that was pretty easy to prove. I'm not going to write it out, but we could prove that one just by doing the sandwich theorem with 1 and 1 over cosine x for the x over sine x functions in the middle. Good or no?
Good.
All right, make sure you have these memorized. Even though I know you can use L'Hopital's rule for them, make sure you have them memorized, because sometimes trig limits and L'Hopital's rule don't work out real easily. Sometimes they do, but not always. So it's good to just know those rules and be able to manipulate the limit to one of those situations. All right, let's do another one. Or let's do a problem here using that rule. What do we need to do here?
Multiply by 5 over 5.
And multiply by 5 over 5. And then we can take the constant, that 5, out. And we should know that the limit as x approaches 0 of sine 5x over 5x is also equal to 1. But if we wanted to real quickly, we could prove that by just letting u equal 5x, because as x approaches 0, u would also approach 0. And we could write this as the limit as u approaches 0 of sine u over u, which is 5 times 1 or 5. I don't need you to write out the u substitution, but that's why this works. Why sine of 5x over 5x's limit as x approaches 0 is also just 1. Good or no?
How should we write it out then if we don't do the substitution?
Just
Cool.
go. Right. Well,
Okay.
go from there to here. It's fine. But always indicate at least that this limit is equal to 1. So at least put in that tiny little step there that it's 5 times 1. Just to show that you knew that to the people on the AP test.
Okay, thank you.
No problem. All right. What about this one? I keep forgetting to change this. This should be a y here. That's the limit as y approaches 0 of sine cubed 4y over y cubed. So I know you're all like, oh, I could just use L'Hopital's rule for any of these, right? But if you're trying to take derivatives of sine cubed 4y, I mean, the first one's not so bad, right? You get 3 sine squared 4y times cosine 4y times 4. But then to take the derivative of that a second time is product rule with the chain rule within the product rule and a huge pain. And then you got to do it again to get down from the 6y to just a 6 in the denominator. And it's just a huge giant mess. So it's better to be able to use the rules sometimes. So what should we do with the cube that is around the sine and around the y?
Take the power out outside of parentheses.
Exactly. Sine 4y over y cubed. And we know that eventually we can just take that cubed and we can pull it outside the entire limit. But first, let's throw in the 4y in the denominator that we need. And what do we need to put into the numerator then?
Four.
Just a 4. And what does that 4 come out as?
64.
64, right? It comes out as a 4 cubed. And then we end up with the limit as y approaches 0 of sine of 4y over 4y cubed, which gives us 64 times 1 cubed, or just 64. Good or no?
Great.
Great. All right. Take a look at another one. Why don't you guys work through this one on your own real quick, because this one would be even more horrible and awful if you were trying to use L'Hopital's rule for it. So go through and evaluate this limit. I'll give you like a minute to do it. Ready, go. hopefully the first thing that you did here was pulled out the 1/4. I think that makes this a little bit easier. And then we can pull out the 4th power from both the numerator and the denominator, right? Making that z cubed to the 4th as a z to the 12th with the 1/4 already out in front, so we don't have to worry about it with any powers. And then, I'll write it in here actually. We need to put in a 3 and a 3, and that 3 comes out from the numerator as a 3 to the 4th, or 81/4, times the limit as z approaches 0. And I'll put all of that inside its brackets now of sine of 3z cubed over 3z cubed, all raised to the 4th power. So we got 81/4 times 1 to the 4th, or 81/4. Is that what you all got?
Yep.
Perfect. Anybody have any questions on that? All right, what about one like this? 2y plus sine 3y over 4y. This is still 0 over 0, right? Still indeterminate.
Split the limit into limit as y approaches 0 of 2y over 4y plus the thingy of the other one.
Plus the thingy of the other one. That is very technically well explained. My 7-year-old from the other room just shouted, "Yeah, I'm right." That was well explained by you. But I think he caught my sarcasm. Yeah, he just said it wasn't. He was very disappointed in your explanation, and you.
Good to know. I will try to improve.
All right. You hear that, Max? He's going to try to do better next time. He says, okay, good. All right. So first one, 0 over 0. This becomes a limit as y approaches 0, then cancel the y's and reduce to just a half. And then this one, we'll pull out the 1/4. And in the denominator, we'll have to throw in then 3 with the 3 in the numerator. We end up with a half plus 3/4 the limit as y approaches 0 of sine 3y over 3y, or 1/2 plus 3/4 of 1, which is 5/4. Good.
So good.
Wonderful. That's just spectacular. Nobody's got any issues, any complaints or concerns or anything? Cool. Let's move forward then. How are we going to find the limit as x approaches 0 of 1 minus cosine x over x? Because this is also indeterminate.
Take the conjugate.
All right, let's multiply by the conjugate. Sounds good. Numerator becomes 1 minus cosine squared x. Denominator we'll leave as is. And using our nice, simple, easy Pythagorean trig identities, 1 minus cosine squared x should become don't all say it at once, sine squared x. Right? 1 minus cosine squared is sine squared. So we got sine squared x over x times 1 plus cosine x. And now we'll just split this up into 2 different limits. One that has a value we know, sine x over x. And the other that gets multiplied by it, which is everything that's left, sine x over 1 plus cosine x. the first limit is 1, and the second limit is 0 over 2, so we end up with 0. Everybody good there or no?
Yes.
All right. And on a separate note here, we will also want to know that the limit as x approaches 0 of cosine x minus 1 over x is also equal to 0. So of the ones we should memorize, this is one, right? That the limit as x approaches 0 of 1 minus cosine x over x is 0, and also cosine x minus 1 over x is 0. Good or no? Good? What about this one? Nice and easy one, right? What do we do with this one?
Do we do the multiply by 10 over 10?
That sounds great.
attempt?
Yeah. Put in a 10. Put in a 10. Pull the 10 from the numerator out. And if we wanted to do the u substitution, we could, but let's just not bother. We get 10 times 0, which is 0. Good or no?
Great.
Great. All right. What about this one?
Oh, that one dude's triangle.
That one dude's triangle.
Pascal.
Pascal's
Yes.
Yeah. This is Pascal's triangle. You should know Pascal's triangle. Everybody good with Pascal's triangle, or should I really quickly rehash that? Okay. So remember that Pascal's triangle gives you the coefficients for binomial expansion. So the fourth row of Pascal's triangle gives you the expansion for a plus b to the fourth. At least it gives you the coefficients for it, which are 1, 4, 6, 4, 1. If the signs alternate from positive to negative to positive to negative to positive, it tells you that instead of it being a plus b to the fourth, it's a minus b to the fourth. So the numerator there should be a minus b to the fourth, with a equal to 1 and b equal to cosine. So this ought to become the limit as x approaches 0 of 1 minus cosine x to the fourth over x to the fourth, which just becomes the entire limit raised to the fourth power, or 0 to the fourth, or 0. Good or no?
Splendid.
That's right. It is splendid. Agreed. All right. Let's do a couple more of these, and then we're going to move on and be done with all of this trig limit nonsense. So we got the limit as y approaches 0 of sine 4y over sine 10y. How can we separate this out?
You can do the limit of y. The limit as y approaches 0 of sine 4y, and then the limit of y as y approaches 0 of 1 over sine 10y. Like separate them.
All right. I'm not going to write the separate limits yet, but yeah, we're gonna eventually write it into separate limits. But yeah, that's good. And in order to turn sine 4y over 1 into something that's easy to deal with, I should probably attach a 4y to it. And to turn the 1 over sine 10y into something I can easily deal with, I should throw a 10y up there. And then let's just see what we've done. We've put a y in the denominator and a y in the numerator. Are we good there? Do we need to do anything else with the y's?
No.
Nope. but we did put a 4 down here, which means a 4 should go up here, and a 10 up here, which means a 10 should go down here. And we can pull out the constants that we aren't using, the 4/10. And now we'll turn that into the two different limits. Which gives us 2/5 times 1 times 1. Good or no?
Great.
Great. All right, before we do this last one, real quickly, what's this limit?
One.
Yeah, why is it 1? Because it could be rewritten as this limit, right? Tangent's just sine over cosine, and I could take that cosine in the denominator as a separate limit, and this becomes 1 times 1 over 1, or just 1. So we want to know this limit is 1, and we also would want to know that this limit is 1. So those are the 6 different trig limits that you should know and memorize and be able to use and apply. Everybody good there or no? Awesome. All right. So let's see if we can separate this one. You guys want to do this on your own or no? No response. Okay. Cool. We'll just do it together then. The limit as x approaches 0. What's that? We'll just separate it out like this, and it's just like the last one we were doing. Put in a 3x and a 4x. The x's are good, but we still need the 4 and the 3. Pull out the 3/4 constant. And we got tangent 3x over 3x. And we got 4x over tangent 4x. And we end up with 3/4 times 1 times 1. Good or no?
Good.
Perfect. All right. Obviously, some of these would have been easier to use L'Hopital's rule with, but I think it's good for us to sort of remember all these rules, especially for the ones that get a little more complicated with L'Hopital's rule. It's easier to do them this way. So that's all we're going to talk about with trig limits right now. We're going to move into talking about limits that equal infinity or limits at infinity. So that will be up next. Remember that if a limit equals infinity, so if like we have a limit as x approaches 2 from the right of 1 over x minus 2, well, as we approach 2 from the right, we're going up towards this vertical asymptote. That limit is infinity. We might say that it's infinity, even though technically a limit that equals infinity doesn't actually exist, right? Because a limit has to equal a real number. So anytime we are looking at a limit at a vertical asymptote that becomes infinity or negative infinity, your answer might be infinity, it might be negative infinity, or it might be does not exist if it was like a multiple choice question on the AP test. So just be aware that these limits that equal infinity technically don't exist. They're not approaching a real number. But anytime we approach a vertical asymptote, that limit will either be infinity or negative infinity, and we'll see if we can figure out, without graphing it, what the one-sided and the two-sided limits and the both one-sided limits and the two-sided limit of this function is at its vertical asymptote. Sound easy enough? Yeah? Awesome.
Yes.
All right. What's the vertical asymptote? X equals
4.
x equals 4. So let's look for the limit as x approaches 4 from the left. As x approaches 4 from the left, that's something like 3.999999999. And 3.9999999 minus 4 is a very small negative. And if I cube a very small negative number, I get an even smaller negative number, don't I? And what is 1 divided by something like negative 0.0000000000000000001?
A really big negative number.
That's right, negative infinity, or technically doesn't exist. But we do know that as this approaches the asymptote from the left, it's dropping down towards that vertical asymptote. And as x approaches 4 from the right of 1 over x minus 4 cubed, well, that's like 4.00000000001 minus 4, or 0.00000000001 cubed, which gives us 1 divided by a very small positive. And 1 divided by a very small positive number ought to be infinity. And if the limit from the left is negative infinity and the limit from the right is positive infinity, we will definitively say that the limit as x approaches 4 of f of x does not exist. Good or no?
Great.
Good.
Wonderful. All right, what about this one? X minus 2 squared. Where's the vertical asymptote?
2.
Equals 2. Good. What's the limit as x approaches 2 from the left of 1 over x minus 2 squared? Well, 1's just a 1. As we approach 2 from the left, that's 1.999999999 minus the 2 is a very small negative. Squared is a very small positive, and we get infinity. And what about the limit as x approaches 2 from the right of 1 over x minus 2 squared? Well, that's 2.000000001 minus 2 squared, which is a small positive being squared, which still gives you a very small positive. And we end up with infinity on both sides. This one is rising as it approaches 2 from the left and rising as it approaches 2 from the right, which tells us we could define this limit as infinity as the two-sided limit, even though technically none of these limits exist, right? Good? Not good? Bad? Great?
Incredible.
Incredible. That's wonderful. Yes. All right. That's all we're going to talk about with vertical asymptotes. Plug in a number very close to the limit and see what happens to it. If it's a vertical asymptote, it's either going to be infinity or negative infinity. But what happens when we plug in x approaching infinity? So for example, for this particular one, what do we get? As x approaches infinity, what does this limit become?
2.
Yeah, it becomes 2 plus something very, very close to 0. 1 over a very large number is basically 0. This is 2. And what does this graph do as the x values get larger and larger? It should be approaching a horizontal asymptote to the right. Okay. So remember that a limit as x approaches infinity is a horizontal asymptote to the right. What about a limit as x approaches negative infinity?
Horizontal asymptote to the left.
Should be a horizontal asymptote to the left. Just because a function has a horizontal asymptote to the right, does that mean that it also has one to the left?
Nah.
Nah, that's right, nah. And just because one has one to the right of, like, say, 2, doesn't mean that the one to the left is also 2. They could either not have one in both directions and only have one in one direction, or they could be different in the different directions. Everybody good with that? Hopefully so. The important piece of this being mainly that a limit as x approaches infinity gives you the horizontal asymptote to the right, and a limit as x approaches negative infinity gives you the horizontal asymptote to the left. So let's take the function 2x squared minus 5 over 3x squared plus x plus 2, and using rules for limits, find this horizontal asymptote. We're going to do the limit as x approaches infinity first. Now, I know that it's infinity over infinity, and you could use L'Hopital's rule, but we could also prove it algebraically by dividing everything by the highest power in either the numerator or the denominator. And that's how the rules for horizontal asymptotes of rational functions were originally developed. So this, if I divide everything by the x squared, becomes a limit as x approaches infinity of 2 minus 5 over x squared over 3 plus 1 over x plus 2 over x squared. And as x goes towards infinity, what happens to 5 over x squared?
It becomes insignificant.
Insignificantly small. It becomes like 0. And what about the 1 over x and the 2 over x squared? Same thing, right? And all we're left with is the limit as x approaches infinity of this constant, 2/3, which ought to be 2/3. And that should help you to remember the rule that if the degree of the numerator and the degree of the denominator are the same for a rational function, the horizontal asymptote is just the quotient of the two leading coefficients. And another important thing is this is just the horizontal asymptote to the right, but for all rational functions, so a polynomial over a polynomial, the horizontal asymptote to the right and the left are the same, no matter what, if it is a rational function. Once we get outside the realm of rational functions, that changes up quite a bit. But specifically for rational functions, both sides, the right and the left, will either have an asymptote or will not have an asymptote, and they will be the same asymptote if it has one. Good or no?
Super.
Wonderful. All right. Here we have the degree of the numerator is less than the degree of the denominator. What should we divide everything by? Still the highest.
X to the 4th.
3. Yep, x to the 4th. Which ought to give us a limit as x approaches infinity of 2 over x squared minus 5 over x to the 4th over 3 plus 1 over x cubed plus 2 over x to the 4th. And as x goes to infinity, everything in this numerator begins to approach 0, and everything but the 3 in the denominator begins to approach 0. So we're just left with 0 over 3 or 0. And that should remind us of the rule that if the degree of the numerator is more than the degree of the denominator, the degree of the numerator is less than the degree of the denominator for a rational function, the horizontal asymptote should be y equals 0. And what's the rule for the numerator's degree being more than the denominator's degree? We should still be dividing it all by the highest power. Which is x cubed. And then this becomes a limit as x approaches infinity of 2 minus 5 over x cubed over 3 over x plus 1 over x squared plus 2 over x cubed. And everything in the denominator is approaching 0. And the 5 over x cubed is approaching 0. So we get 2 over 0, which is undefined and tells us there is no horizontal asymptote in either direction. Everybody good with that or no?
Wonderful.
Great. All right. Take a look
Will
at
we
this
have to
one. and
find
see
the?
if- Oh, go ahead.
Sorry, but will we have to find the slant asymptotes at any point? Or
No.
okay, cool.
I mean, you should know how to just divide. I mean, just do the long division and it tells you what it is. Drop the remainder, but no, you don't need to be able to find those.
All right, thank you.
All right.
You
So
want
take a
us to
second.
say,
Go ahead.
wait, you want us to say that it's for both sides, right? Yeah, I want us to note that out each time for a rational function, like in an
Yeah.
answer.
Yeah, you should just state that it's in both. Just write in both directions is good enough. Okay. Let's think about this one here for a minute. Root 9x squared plus 2 over 4x plus 3. As we go towards infinity, what happens to 9x squared plus 2? Does that 2 matter much at all?
No.
No. And so what does the square root of 9x squared become?
3x.
Almost. Remember, the square root of x squared is equal to the absolute value of x. So this is the absolute value of 3x over 4x because the plus 3 becomes insignificant. And now we have to take into account our definition of absolute value. Is our x value greater than 0?
Yes.
Yes. So the absolute value is just the thing that's inside of it. Cancel out the x's and you get 3/4. Y equals 3/4 to the right. But when we do the limit as x approaches negative infinity, since x is less than 0 now, when you take the absolute value of 3x, you're taking the absolute value of a negative, which means you take the opposite sign of it, negative 3x over 4x, which gives you negative 3/4. And so we have y equals negative 3/4 to the left. And it's okay to have different horizontal asymptotes in the directions. Good or no?
Can we skip the part where you wrote the limit as x approaches infinity or negative infinity of the constant? Or do we need to write that out as well?
Nah, if you skip that, that's fine. Anybody having any issues? Everybody good so far? Let's see. I don't think we're going to make it through. Yeah, I don't think we're going to make it through everything with E and natural log, seeing as having only about 10 minutes left. So I think we'll probably just stop there for today.